Hey guys, hope you're having a fantastic day. We will be talking about derivatives and rates of change today. This is lesson 2.7 in our calc book. You have to maybe reel me in a little bit on this. I get a little bit excited when I start talking about derivatives. So if I get too excited, you might have to shake me down a little bit, make sure that I know that this is still a calculus class and there's no reason to get that excited. I want to revisit the idea of the tangent line. Okay, remember that the tangent line, if I have a curve, I'm just going to make one up right there. My tangent line is going to be just a line that intersects the curve at one point. That's the best I can do. Really, it's a tangent line because it touches it in one point. Do I need to move that point? I think if I move that point, it would help me. Uh-oh, I'm moving the line. Leave the line there. The line looked good. I'm trying to move the point. Let's do that. I feel better with that. You feel better with it? I do. I don't feel good with moving slides already, but we can go back. Alright, so that tangent line right there is going to be there because it's only touching that red line in at most one point. And so to help me out with this, what I did was I'm interested in where it's touching right here at point P. Okay, I'm actually going to move that point P to up here at point P. And so where point P landed at, that was my A. And the whole idea with it was that I was going to select a Q that was close. Okay, so I was going to choose a Q on that curve. Maybe I'll just choose it right here. And we kept on making it so it got closer and closer and closer to that point P. And so wherever that Q landed, I'll just put it starting right here, we called that X. So eventually what I had was my X was approaching A at that point. Now the difference between these 2 points right here, Q and P, the vertical distance between them can be labeled as f of x minus f of a. This is just my f of x value, and then right here is where my function value at a. And so if I put all this together, we found that the slope of this was just going to be my f of x minus the f of a over x minus a. But keep in mind, we tried to make it so Q got closer and closer and closer to P. And so what that turns into is it turns into a limit. And the limit's going to be as x approaches A. And so this is going to be a very helpful limit going forward. So much so that it fills in the blank right here on this slide. The tangent line to the curve y equals x at the point PA f of a is the line through P with this slope. So we're getting to use this same slope, provided that the limit exists. So let's see how this helps me. We've worked this problem. We worked this problem the long way on a previous video. And so I want to find the equation of the tangent line to y equals x squared at the point 1, 1. I remember drawing it. And so we found the point 1, 1, and I wanted the equation of that tangent line. Maybe in class we'll go back and we'll find what the answer is, and we'll see if we can work it a little bit better now. So in this case, my A is going to be 1, and then my f of A would be this f of 1 right here, which is just 1. So my function value is going to be this x squared. So plugging this in and finding the slope now, my slope is going to be the limit as x approaches A. Well, in this case, A is going to be 1 of my function f of x minus f of 1 over x minus 1. Pretty much what I did was I took that definition of the slope of my tangent line from the previous slide. I took out all the a's and I put 1 in their place. Okay, now let's have it make sense with the current problem. The limit as x approaches 1, like I said, f of x was going to be my x squared right here. So x squared minus f of 1, well, f of 1 is just going to be 1, over x minus 1. We're in the same problem that we've had over last few weeks, is that if I plug in 1, it gives me a 0 over 0 in indeterminate form. But I can factor the top. Okay. And so that's going to make it so my x minus 1's cancel. I have a well-behaved function I can plug into. And so the slope of my tangent line is going to be 2. I've got a slope, I've got a point, I've got point slope form. So y equals, distribute the 2, add the 1. I'm feeling weird about that. Give me a second. Yeah. Y equals 2x minus 1. There we go. Now, sometimes when we're working our limit function, I erased all that from earlier. So let me draw it back real quick, right? Or something similar to it. It won't be exact. Sometimes when we're working this, we have point P right here. Q is on here and it's sliding down towards P. What we do is we take this X and A difference right there. Whatever that difference is, we let it equal H. So that's going to change some things. If I let this difference right here between these two equal H, then I could add A to both sides and I get A plus H. Meaning that I have a new definition for my slope. And this is one that I tend to use more in class. The limit as H approaches 0. And normally it's f of x. But now remember x is going to be A plus H. Minus f of A all over x minus A. Well, x minus A is going to be H. So now we have a new, and I think for the most part, a better definition of the slope of a tangent line. So we have this, what is that? That's like a rational function, hyperbola, 3 over x at the point 3, 1. I want to find the equation of the tangent line there. I'm going to use my new formula, that limit as h approaches 0, and see if that looks a little better to me. Okay. So we do have this point right here. There's a couple ways to work this. I might work it different in class than what I'm doing in this video, but I'm going to go ahead and just plug in 3 in for these a's. And so I have f of 3 plus h minus f of 3 all over h. So how does that help me? Well, now I can take this 3 plus h, and it's just going to go in for the x right here. Okay, because remember, this y is the same as f of x. So I have 3 over 3 plus h minus f of 3. Well, if I plug in 3 right there, it gives me 1. And I also have a 1 right here. So I can get 1 from either of those places, all over h. A couple different things we could do here. I'm just going to find a common denominator up here on top. So I'm going to put it all over 3 plus h. And I'm still going to have that all over h down here. So here, I didn't change the denominator at all, so my numerator is going to stay the same. Just so you can kind of follow where we're going here. There's the minus sign coming down. And this was 1 over 1. So I multiplied the bottom by 3 plus h. So I need to multiply the top by 3 plus h. So, it's looking messier and messier, but I think I can clean it up some now because I got 3 minus 3 right there, and that's just going to leave me with a negative h on top. Okay. Over 3 plus h. And instead of dividing by h right there, I'm going to multiply by the reciprocal, 1 over h. I think that shows a little bit better where these h's will cancel. And now I'm just taking the limit as h approaches 0 of negative 1 over 3 plus h. If h is going to 0, my limit has to be negative 1/3. And again, that's my slope. That's what my slope's equal to. So I got my slope, I've got my point, I'm ready for point slope form. So I'm just going to do y minus 1 equals my m times x minus 3. So I get y equals negative 1/3 x. Let's see, if I add 1 to this, negative 1/3 times negative 3 is positive 1. Yeah, it's just 1 plus 1 is 2. And that would be the answer. Now there is another way to work it that makes a little bit more sense even than, I think plugging in these 3's right here can make it a little bit crazy the way it works. Okay, so there is another way that we can work it, and this problem sets it up well. Again, I can do all this with that first definition of a slope that I had, the limit as limit of f of x minus f of a over x minus a. I can work with that, but you're going to see me using this one a lot. I like the h one. Okay? So I'm going to go ahead and write it down again. And as you can see, I have 3 points flying through on this. I can't plug in all 3 points at once. So I'm going to show you the shortcut, the way that I normally work it whenever I see a problem like this. And what I do is I don't plug in any numbers in this. I leave a lot of variables. Okay, so I'm going to plug in a plus h into this x minus, I'm going to plug in a. So yeah, it looks a little bit messier, but maybe it would either be that or you could plug in a 1 in for these a's, but you'll see you have to rework a lot of stuff in just a minute. See my shortcut on this. I got a conjugate that needs to happen. So whenever I multiply by the conjugate, the top cleans up tremendously. But that's not an h. It would be an a. And the bottom, I'm still using the rule that whenever it comes to simplifying the bottom, I'm just going to say no. Even if all the cool kids are doing it, and they all have hair and they're not bald like me, I'm not going to give in to that temptation and simplify the bottom. So that's going to make it so those a's cancel. And I'm going to go ahead and save. I'm going to save a little bit of room here. Now my h's cancel. I just have a 1 on top. So I have 1 over the square root of a plus h plus the square root of a. And remember, if h is going to 0, like this limit says it is, then I simply just have 1 over 2 square roots of a. Very interesting equation right there. We're going to be messing with that a lot. So what was the benefit of not plugging in a 1, 4, and 2 into this? Remember, because all of these are actually a's. Well, now, it just asked me to find the slopes, not the lines. To find the slope at 1, at a equals 1, I just have to plug that into my slope equation. It would be 1 over 2 times the square root of 1. 1/2. At a equals 4, isn't it nice they were all perfect squares? 2 times 2 is 4. And then at 9, I think you see where this is going. 1/6. And that would be the slope of each one. See, if I did plug in 1 right here in the beginning, and then I would have to work it all out, and yeah, this would give me the slope right there. But then I have to go back and I have to work it. I have to plug in 4 in from the beginning, and then plug in 9. So I'm doing all of this work over here 3 times, 1 for each slope. Whereas if I just get my generic form of my slope right here, where I can just plug in any number, whatever number it asks me, I can just plug it in at the end. And I think that way is a little bit more efficient on a problem like this. Velocities. It did say velocities, I promise. You couldn't read it through all that. I could barely read it. That was a blank slide. Velocities. Alright, so when we're working with velocities, we're looking at a very similar equation. Okay? We found velocities very similarly back in section 2.1, and we're going to do it very similarly here again. Except for they're going to use h every now and then, where h is going to be this distance between these 2 times. Okay? And so whenever I work that, I can then plug it into my velocity equation, which if I'm looking for average velocity is just going to be the amount that the object moves over the time elapsed, which would just be f of a plus h minus f of a over h. As you can see, the drawing right here is very similar to what we just did. So it's going to be very similar to finding the slope of the tangent line, even the same formula right there. So I'm going to be interested in calculus and finding the instantaneous velocity. Remember, we dropped a ball off the CN tower back in 2.1, and we were able to calculate how fast it was moving at 5 seconds. We're about to do that again, but if I'm looking to find the instantaneous velocity, v of a, then I'm still going to be using that f of a plus h minus f of a all over h, but once again, I'm going to make it so the limit is as h goes to 0. Alright, so let's drop the ball. It's going to bring this down. Again, my equation of motion on this, it's not given. I would give it to you if you were to see something like this on an assessment. And I've assigned problems where it gives you an equation of motion. But for Earth, it's 4.9 t squared. And it's asking me to find the velocity of the ball after 5 seconds. So I'm going to use the trick where I don't plug in 5 until the end, just like I did on the last example. I think that works a little bit better. So, my velocity is going to be the limit of this. I guess I could have pulled that down, but that's just going to be, well, I'm just going to plug in a plus h in to this t. So that'd be 4.9 a plus h squared minus f of a. Well, it's just going to be plugging in a in for that t. 4.9 a squared, and then it's all over h. And I didn't write my limit in here. I am taking the limit as h approaches 0. So I got some cleaning up to do. So the first thing that I see that I want to do is I'm going to go ahead and distribute all, or I'm going to expand this binomial. So a squared plus 2ah plus h squared. I got the minus 4.9 a squared on the end. Still got the limit rocking right there. If I distribute this 4.9, I get 4.9 a squared plus 9.8 ah plus 4.9 h squared minus 4.9 a squared all over h. Still rocking the limit. I got my 4.9 a squareds to cancel. And as you can see, everything that's left has an h in it. So I've got h times 9.8 minus 4.9 h. And that's all over h. So now my h is canceled. So I'm left with the limit as h approaches 0 of 9.8 times negative 4.9h. And if h is going to 0, that's going to knock out this whole term, because 0 times the 4.9 would just go to 0. And so I end up with my velocity at whatever seconds I want to would just be 9.88. Does that 9.8 sound familiar? Something about acceleration due to gravity? All of my physics people? Hopefully it does. And so to answer the question, at 5 seconds, all I got to do now is plug 5 in to the end. And so I get 9.8 times 5, which gave me the same answer that it did a couple weeks ago, 49 meters per second squared. How fast is the ball going when it hit the ground? Well, when did the ball hit the ground? It's a good question. So to figure out when the ball hit the ground, I can just take its position up here at the top, and it would just be where its position is equal to 0. I'm sorry, it wouldn't be 0. It'd be where its position changed by 450. Sorry, I'm going the wrong way. So it'd be after the ball had moved that 450 meters. And so if I divide both sides by 4.9, I get 450 divided by 4.9. I'm going to do the lazy man approach on this. Take the square root of both sides, and that gave me around 9.6 seconds. So how fast is the ball going when the ball hit the ground? Well, the ball doesn't hit the ground until 9.6 seconds. I can tell you how fast it's moving at 9.6 seconds. I just got to take the 9.6 and multiply it by my 9.8. And so when the ball hits the ground, it's going about 94 meters per second. So whether we're talking about this instantaneous velocity or we're talking about the slope of a tangent line, it all fits under this big idea in calculus that I finally get to say. I've been wanting to say it all video. They're all called derivatives. This whole idea of taking the limit as h approaches 0 of f of a plus h minus f of a all over h, whether I'm doing instantaneous velocity or whether I'm doing the slope of a tangent line, is called the derivative. Okay? Like I said, they're both similar equations. So I'm taking the limit as h approaches 0 of f of a plus h minus the f of a all over h. And I don't want to forget about my other guy. I can still be using this first formula. If I see it's going to help in the problem. How can I see if it's going to help in the problem? Well, maybe I work it with all these h's and it's just not going anywhere. I might jump ship and go try it with this other way. Okay. I think that this bottom box is the same thing I was using up here at the top. So I just went ahead and put it up here at the top. So we have both formulas. So instead of saying find a formula for the slope or find a formula for the instantaneous velocity, I can just say find the derivative, and that's what that means. Okay. And so I can just take the limit as h approaches 0 in pre-cal we call this the difference quotient. And I'm going to let you try this. Okay, I'm going to work it out as well. So go ahead and hit pause on the video, and then you can follow my work if you don't get the same answer. I've got 2a minus 8 on that. Okay? A couple things to be careful of. Make sure you're plugging in a plus h in for both of these x's, and that you leave room, put some parentheses up to distribute that negative through. Okay, what if I'm wanting an equation to the tangent line? already, oh goodness. Oh, I went straight to the end, didn't I? Is this where we are? The derivative, we're past that. We're there. Equation to the tangent line. So on this curve, x squared minus 8x plus 9, it touches the point 3, negative 6. And so again, remember, this is my a right here. So to find the slope of it, I just have to plug it into my derivative. And you know what, guys, I apologize. I haven't been good about my notation on this. This is called f prime of a right there. That little line right there, that little accent, we'll call it, is a prime. And so if I'm looking for the slope at 3, I can do what I did earlier and just plug in 3 in for my a. And that gives me a negative 2. Something tells me it should have been a positive 2. 6 minus 8. Oh, it's negative 2. We're good. And so now I've got my slope. I've got a point. I got my point slope form ready to go. So that'll be a plus 6. And then negative 2 times x minus 3. So I'm going to subtract 6 from both sides. Oh, they canceled. So the equation of my tangent line to this parabola that would go through this point would be y equals negative 2x. Now, there's a lot of other rates of change. We've been doing a rate of change to do slope. We've been doing a rate of change to find velocity. But derivatives aren't just limited to finding slopes and velocities. It happens a lot. Okay? And so whenever I'm just talking about a rate of change, we're just talking about a difference quotient. It's just going to be how two y's change divided by two x's. And if I don't have that limit in there, it's known as an average rate of change. Okay? And so I can find it very similarly to how I've shown previous in this video. So we consider the average rate of change over smaller and smaller intervals if we let x1 and x2 get closer and closer. And that's going to make it so delta x goes to 0. Same as my h going to 0. Suddenly now I don't have an average rate of change. I have something called the instantaneous rate of change of y with respect to x. Okay? And so I can interpret it as a slope of the tangent line to the curve at that point. So another way we can write it, so if I'm taking the instantaneous rate of change right here, it would just be the limit as x2 gets close to x1, or as it approaches x1, of my slope formula, or my rate of change formula is a better name for it. So suppose I have a manufacturer of bolts of fabric. I think that's the things that are at Hobby Lobby that has the fabric wrapped all the way around it. And you go up there and say, I need this many yards of it. It has a fixed width, and the cost of producing X yards of this fabric is some function of X dollars. I want to know the meaning of the derivative f prime of X in its units. Okay? So the meaning is, this is just going to be the instantaneous rate of change of my y with respect to x. So if I get rid of that y and I call it cost, and I get rid of that x and I call it bolts of fabric or yards produced, then what the f prime of x means is the rate of change of production cost I guess it wouldn't be costs, it would just be singular, with respect to the number of yards produced. And so to get its units, I'm going to come up here for the units. Remember, my f prime is going to be the change in y over the change in x. Well, y in this case is going to be my cost, and then change in x is going to be the number of yards of fabric. And so cost, we normally measure in dollars. And this fabric, we're measuring in yards. So my units on that would be dollar per yard. So in practical terms, what does it mean to say that f prime of 1,000 equals 9? F prime of 1,000 equals 9. Keep in mind, this is my x, and this would be my c, because that's what it's equal to. So x is my yard, so I could say after producing 1,000 yards, the rate of change of production increases $9 per yard. Or maybe just like a more simpler version of that, you could even say the cost of manufacturing the 1,000th yard is going to be about $9. I'm going to skip part C. I might talk about it in class, but I don't think we need to have it going forward. Okay. All right, let's look at this national debt and see if we can do some stuff with derivatives on it. So debt is going to be that D of T column, and we got time T, so it'll be 1980, 85, 90, and so forth. I want to estimate the value of D prime of 2,000. D prime of 2,000. It might be good to interpret it first, because that's just going to be how fast the debt, the national debt, is changing in the year 2000. So it's giving me a snapshot there in time of how fast the debt's going up or the debt's going down. And so to work this, I need a calculator, because I've worked a different year in my notes, but I'm going to use this 2000 right here. And so to work this, I'm going to do what I've done before. Is I'm going to choose these points that are really close to it. And so I am looking for an instantaneous rate of change because I have this prime right here, but I don't have a function to help me out. And so an average rate of change is going to be as good as I can do on this. So I've got 56. So how do I write that? So what I'm doing is I'm taking the limit. Am I on the right color? Yeah. I'm taking the limit as the time approaches 2000. And the best I can do with that is going to be this average rate of change. D of, see, it's getting close to 2000, so I'm going to use 1995 over T minus 1995. And so if T's approaching 2000, I'm going to plug in my 2000 numbers in right here. And I'm going to plug it in, let's see, 5674.2. And I'm going to find out what that average rate of change is just from 95 to 2000. So 5674.2 minus 49.74. I'm going to divide that by 5. And so it gave me 140.04. Okay, now I'm going to do an average rate of change from 2000 to 2005. Again, it's going to be the limit as t approaches 2000. And I'm going to do a d of t minus this d of 2005 over t minus 2005. So again, it's just an average rate of change. I'm just going to plug in what I got from this table. So that's going to be the 5674.2 minus d of 2005, be 7932.7, give me a big nasty number. If I divide that by -5, I get 451.7. So the best I'm going to be able to do to actually find what the national debt was changing by in the year 2000 is going to be to take these two numbers and just simply average them. So I got 140.04 and I have 451.7. If I take the average of those two numbers, 140.04, 451.7, divide that by 2, 295.87. And that's in billions. So we can say, like, in that year 2000, the national debt was increasing by $295.87 billion. Seems like a lot. So this is the current year's problems. Take a look at those. Work the ones you can. If you can't work them all, you have some questions, make sure you ask. I will catch up with you guys next time.